Back to Bal Vigyan Bharati with Abhilash Sarkar. We'll move on to the problem number 40 in fluid statistics. Next, the 40 problem says this is an arrangement of differential manometer that is used for measuring pressure inside a pipeline with any fluid flowing inside. In this case, it is air. So, this is kind of open ended U2. Other end is attached to the pipeline where it is that air is there, and there is some liquid which is being deflected due to this pressure. There is a height difference. If I take this reference of this arm, this will be the state of fluid. This is not the level. I'm just matching the datum on the other arm. So this is like that. So at any point there, if I say the center point basically, so this is 4, this is 0.3, this is 2, and this is 1. The height difference is delta H, which is given as 70 centimeter, and 4 to 3, this is L, is given as 140 centimeter. Okay, this is media is air and this media is water. Okay, these are the information given. So you have to find P4. What is the value of P4? The other things given is find the specific gravity of water at this air is said to be at 20 degrees centigrade, and that's why the specific gravity of water at 20 degrees centigrade is given as some value as given 9790 Newton per meter cube. This is given. Okay, and P atmospheric is assumed to be at P1, and that can be assumed as 0. So atmospheric pressure is not considered in this only. So in this case, what are the equations can be formed if I compare these points where the liquid is same and they are in same datum. So P3 is equal to P2, we can say. So this arm, this is liquid arm. So P3 and P is 2 if I say. So P3 from there, we can say that this is pressure at P4 plus the difference between this air column L and row of air, or this not given. Let me check here. And this of air also has to be given. This is not given. So that can be taken as rho into G. That means normally it is this is equal to 1, what we can say, this is equal to rho of air is not given. The density of air that has to be referred from somewhere. that I think during theory class I have given, it is 0.0073, that was kg per meter cube. This into the g is 10, if I assume approximately 10, so this will be 0.073, and this is meter per second square, so the kg meter per second square Newton per meter cube. So this much will be the air volume. Okay, you can refer my old previous videos where theory class explained this value of air. If so far I remember, it was this much. There may be 3 or 9 something. So this is approximately the air, the specific the gravity, that density is given this much. Now if I multiply to g, I'll get specific gravity of the air. So this is okay. So this is L into rho of air, means gamma of air. So this will be the pressure, and this case in P2 side, this will be the atmospheric pressure, means P1, the pressure atmospheric, plus this delta, and this is caused due to the water. So this is the specific gravity of water we have to take. Okay, so this will be the equation. Now this is said to be 0. This is said in the question itself, so you can consider it as the comparatively the atmospheric is 0, or else if you can even take, that value will be 10 to the power 5 Newton per meter square as per the standard 1 atom. So that P4 will be what? Delta H is equal to 70. To water it is given as how much? 9790, minus L is 140. I am taking this side, into 0.073. Okay, so this will be the case. Now this part is very much negligible, if you can assume. So this is only caused due to this. Okay, what is this? This is due to the water column being deviated. So if we calculate, this will be something. This is meter into Newton per meter cube. So this will be Newton per meter square, whatever the value will come here. So this will be your P4. Okay. So these are some practical example. Means normally people calculate by seeing physically this arrangement. This arrangement are there in any kind of process plant where air being used. So what is the pressure? What is the pressure difference? This is the P4 to, you can say, the pressure here. So with that difference you can assume the pressure here, and later on when you go for the fluid dynamics, there if this air is flowing instead of being stagnant, then you can find this kind of arrangement will help you to calculate the velocities of the fluid flowing inside, and from there how much flow you can calculate also. So these are the possibilities of this such arrangement. Okay, so we move on to the problem number 41. So those values of the specific gravity or density of air, some of the cases you have to remember. Kerosene, water is definitely yes, and glycerine. Such some of the values you have to remember, because that may happen that in question or in the exam those values are not given. These are very common values that can be remembered. So kindly try to remember those values. Okay. 41. What is saying? A candle of diameter D is floating on a liquid in a cylindrical container, cylindrical container, okay, of diameter capital D, where capital D greater than small d, as shown. I will show you the drawing or the sketch that is there in the question. Okay, in the figure, if it is burning at the rate of 2 centimeter per hour, then the top of the candle will move at what rate and in which direction. Okay, so the arrangement is, there is a cylinder full of fluid. Let's say this is being leveled up to this. There is a candle which is in equilibrium and vertically, and it is burning. Okay, this is the candle is submerged in the fluid by the equal length in and out. So the length which is inside the fluid and which is outside the fluid are of equal length, and this is floating in steady state, and it is burning. Okay, so now this is burning at the rate of 2 centimeter per hour. So that means it is burning, it will definitely reduce its length, basically its diameter will be same unless it is burning, and throughout the length its diameter is same. So while it is burning, it will burn keeping the diameter intact. That is the assumption you can take. So until up to which it is burning, that is only the volume is melting and it is going out of the scene. So if it is burning, so what would be the rate of its movement? What is the ask? What is the rate? This is the rate of burning. Then the top of the candle will move at what rate? So it will move, definitely move, but it at what rate it will move and in which direction. Okay, so let me think that in hour it is reducing 2 centimeter. Okay, So what would be the length for it after 1 hour? After an hour, the length will be somewhat 2L, the initial length minus 2. Okay. So when it is burning, so that means the center of gravity is at the line of the datum is equally so much. So that means line of that means the weight of the candle and the buoyancy due to the movement due to the disbursement. Let's say this is L. What is the area of that pi d square by 4? This much of area. This is the volume into the density of water into G. So this much, this will be the same. Okay, weight. This is weight when it is initially floating before it started burning. When it started burning after an hour, this will be the length. And if it is the case, our equation after an hour will be the W2, and it will float in this after even burning. It will float in the steady state, if I can assume, because this is not deflecting anywhere, only it is burning and reducing its mass. So that weight after 1 hour it will reduce, and that will reduce up to this. And what would be the case for that? What would be the case now? I don't know the what would be the age. So this is really the W2, and this case, what will be the length inside? Let's say I'm assuming it is something L2, and this is pi d square by 4 into rho of water into G. This will be the case for equilibrium. But what is the W2 there? W2 is the weight is 2L minus 2 this into the area of cross section, this pi d square by 4 into the density of the wax, we can say wax, into G, and this is equal to L2 into pi d square by 2 by 4 into rho of water into G. So in this case, these are not taking part, G not taking part. And for the first equation, this was 2L into pi d square by 4 into G, rho of wax into G. This will be the equation, and this is the, so in this case also this will minus and G will minus. So what are the equation for the first case? It will be L I know for first case because L is there. So in this case, rho of 2 of rho of wax is equal to, what is the L will be cancelled out for the first equation, rho of water. This will be the case. Now in this case, the first from the first condition we can establish this relation, 2 of rho of wax is equal to water. Okay, now if I go there, 2 of L minus 2 and rho of wax is equal to, if I put rho of water by 2 is equal to L2 into rho of water is there. So this will be cancelled out. So 2L minus 2, that is equal to 2L2. Okay, so 2L2 is equal to, L2 is equal to L minus 1. So what I assume after an hour, if it is burning at the 2 centimeter, so my new state will be, if I can draw it just beside this, the condition. So what it says, the L2, this was L2, and for the equilibrium, the equal height will be there outside. So this is your L minus 1 I am getting. So this also will be L minus 1. So the top, earlier it is L, now it is L minus 1. So that reduction in height is equal to L minus 1, the top. If I take the reference from here, because this level is not changing, water level, So the reduction in height is equal to L. So this is 1 centimeter. So the top I can say is moving with a 1 centimeter per hour, because this is the scenario after 1 hour where the wax is being burned at rate of 2 centimeter per hour. So this is the 1 centimeter per hour, and which way it will go? Now this, if I take the reference with this has come down. So that means wax is going down. So the direction will be downward. This is downward. Okay, so wax is, the top of the wax is going down at the rate of 1 centimeter per hour. Understood? Okay. So we'll move on to the problem number 42. Next problem is here, number 42. So that 42 problem says an ice block contains a glass ball when when the ice melts within the water in water containing in a vessel, what would happen to the level of the water? Okay, this kind of application problem will come very frequently in competitive examination. So let me draw the arrangement. The arrangement is something like that. At the vessel, there is a water level, maybe water level of this height initially. That maybe you can say that is of height capital H. When ice cube along with a ball inside, a glass ball is dipped inside. So that means this is the case. This is your ice ball. So this height may rise or not so, maybe rise up to of height, let's say h1. Okay. Now the third scenario is that when ice melts, there could be a rise or fall in the height of the water level from this increased level. That could go high, that could go down, that would be same, or rise or fall. So out of this, what would be the situation that we have to derive? So the first situation first, when ice with ball, if it is the case, then the mass, the water height will increase due to this volume. Equivalent amount of water being displaced, means when it is button flow, when the arrangement will float in the water, it will definitely disperse some water, and that disperse of water will cause to rise a height in the level. So the mass of water displaced, you can say, is equivalent to the mass of the ice plus mass of the glass ball, you can say, isn't it? Mass of the glass ball, you can say. So the mass of the water dispersed will depend on let's say the mass of the water displaced VW and the water density is rho W. You can assume ice. This is now ice externally. If I think this is a dimension, this is a cube. If the dimension externally, even though it is ball is there, the external dimension, whether ball is there or not, the external dimension will be same. So the ice volume will be the mass of the ice will only be the volume responsible for this mass is Vi minus Vg, because G part, it is not the part to decide the mass of the ice. So mass of the ice depends on the dimension, external dimension, that is, if I say Vi, the physically, that has to be that volume of the glass has to be deducted from that to get the exact volume of ice, and if it is converted into mass, that will be multiplied with its density. This is the density. Now plus the mass of the glass ball is, we have taken the volume and the density of the glass ball. This will be the equation. Now the volume of the water will be, now if I divide it, Vi minus Vg rho I, this with this rho I have to divide the full thing, and definitely I will get volume of, and this I am denoting as VW1, because second case there will be another volume. What is that volume? This is the volume when ice is there. Now when ice melts, this ball, the glass ball, having higher density than the water, and it will dip inside. In that case, this will occupy the equal amount of volume. So in second case, if I say VW2 with the volume of water, the volume of water increase, means water increase in what sense? That this glass will occupy equal volume, so that will disperse. So that is the volume increment in water due to the glass is being dipped. So that is equal to, glass equal to Vg will be the volume, definitely equal volume, and the volume increased by the ice being melt. So ice being melt, the ice volume was exactly Vi minus Vg. This was the ice volume, and that when melt then how will you convert it into the water? The conversion of volume, if it is the volume of ice was there, now this I cannot correlate directly the volume. Rather, if I say that the mass of the ice will be equivalent to the mass of the water even after melting. So from this sense, whatever volume of ice will be there, this is the volume of ice. If I multiply it with the rho of ice, whatever it will give the mass, it will be same as the water volume. Let's say I am talking about V dash volume into the rho of the water. If I can get this, well, this is my assumption. This will be the converted volume of water when ice melts, because at the end mass will not be lost. Mass of the ice melting, after melting, will convert into the equal mass of water. So the mass of ice, I will get the volume of ice, exact volume of ice into the rho of ice, that I have done here, and that will be converted to equivalent mass of water. The equivalent mass of water is equivalent the converted volume into water into rho of water. So exactly V dash W will be the case here when V dash W, this I need, because this volume increment is due to the dipping of glass and the conversion of ice. So then water conversion equivalent amount will be Vi minus Vg into rho I by rho W. This will be the converted water when ice being melt, equivalent ice. So this will be the rho I by rho W. So this will be the second set of volume. My situation is that ice is melt. Ice melts down. Okay. So when ice melts down, two things we have understood, that a glass ball, as though it is as because this is having higher density, will dip into the water and it will occupy the equal amount of volume, that is Vg, and ice melts will convert into equivalent amount of water when we will equalize the mass, because straight away you cannot assume about the volume. So if we equivalent the mass we equalize, then from that we can get the volume. So this is the first equation, this is my second equation. Now out of this, which one is higher, to decide I will take the difference. If it is negative, then I can say this is lesser. If it is positive, I can say other one is lesser. So I will take the difference. So VW1 minus, I am deducting this. So out of this, you can see this part is same in both, isn't it? So this will be deducted. So this can be deducted. What is remaining? This part of VW1, this part of, so this will come first. Vg, rho G, rho W. This part will come second as a negative, is Vg. So this will be my ultimate part. So I will rub all this part. Okay. So now what is remaining here? If I take Vg common, this will be rho G divided by rho W minus 1. Now as we have seen, this is glass ball having more density than water, and this is density of, this equation is correct. This is higher density than water, water is higher density than ice. So rho of G by rho of water is greater than 1. So this is something multiplied with the factor T, where T and this minus 1, so that means this minus 1 is greater than 0. So this part is positive, so ultimately T is positive, so this is total part is greater than 0. So that means positive result. So positive result does means what? How will I get that positive result? This minus this is greater than 0. So that means VW1 is higher than VW2. This implies what? As the cross section is same, the height for first case, if I say H1 is raised into the cross section A, will be higher than H2 for the second case into the cross section, which is same for both cases. This cancelled out. H1 is higher than H2. For first case, when ice was there, the height raised by the water due to the dispersion of the water for this arrangement is higher than the height which is caused when ice being melt. So my answer will be fall. There are 4 options, whether it will fall, rise. So my answer will be, there will be a depression in the water level. That means water level will come down. Understood? So there are in my this session, in next session I will move on to problem number 43. So keep watching this. Kindly revise this problem and understand what is the concept behind that. These are very beautiful and interesting problem, and these are very regular problem in competitive examination. So better go through this problem and you will definitely get good concepts. Thank you.